Our first example problem here asks us to write the sine, cosine, and tangent ratios for both angles H and angle F. So to do these ratios, we have to remember that there's a nice little mnemonic for sine, cosine, and tangent that's called SOHCAHTOA. SOHCAHTOA. And it tells us that to write the sine ratio, we take the opposite leg of the angle over the hypotenuse of the triangle. For the cosine ratio, we take the leg that's adjacent to the angle and put it over the hypotenuse. And for the tangent ratio, we take the opposite leg and we put it over the adjacent leg. So let's start with angle H, and let's start by doing the sine ratio for angle H. So we're going to do sine of H, which means that we're going to take the opposite leg length and divide it by the hypotenuse length for H. So the leg that's opposite angle H would be this side right here, segment GF. So we're going to take segment GF's length, which is 12, and now we're going to put it over the hypotenuse length, which we can see for this triangle is 15. So we have 12 over 15. When we have these fractions, we want to reduce them if possible. So if I divide both 12 and 15 by 3, I'm going to get 4 over 5. So the sine ratio for angle H is 4 over 5. The cosine ratio is next. So the cosine of angle H is going to take the adjacent leg divided by the hypotenuse. So the leg that's adjacent to angle H, remember the legs of the triangle make the right angle, so these two parts are the legs. The one that's adjacent to angle H is segment GH with a length of 9. So that's going to be my numerator. And the hypotenuse is 15 again, just like it was for sine. And then I'll divide both of these by 3, and I'll get 3/5 for the cosine. Lastly, we'll do the tangent for angle H. I'll come up here and do it. The tangent for angle H means take the opposite leg and divide it by the adjacent leg. So again, opposite leg for angle H was 12, and adjacent leg was 9. Divide both those by 3. The 12 divided by 3 gives me 4. The 9 divided by 3 gives me 3. So the sine for angle H is 4/5. The cosine for angle H is 3/5. And the tangent for angle H is 4/3. Now we're going to look at angle F. We're going to do sine, cosine, and tangent for angle F. Some people might think that, well, those are just going to be the same because it's the same triangle. So isn't the sine of angle F going to be just like it was for the sine of angle H? And the answer is no, because now the opposite leg for F is 9. That was the adjacent leg for angle H, but because we changed our perspective, now we're looking at angle F, now the side that's 9 is opposite our angle. So when we do opposite over hypotenuse for angle F, it's going to be 9 over 15. Hypotenuse isn't going to change. Hypotenuse is not relative to which angle you're looking at. Hypotenuse is always the longest side. It's the side that's across from the 90-degree angle. So that won't change for angle F as compared to angle H. But the opposite leg will. It'll become the 9. And so we've already reduced this. We know it's 3/5. The cosine for angle F, now the adjacent leg is 12 and the hypotenuse is 15, right? Adjacent to the angle F is the side that's 12. Hypotenuse is still 15. So 12 over 15 would give me 4/5. Tangent ratio for angle F. Now, that's still opposite over adjacent, but again, opposite for angle F is now 9. Adjacent is 12. So that's going to be 9 over 12, which is 3/4. So I think I mentioned this in the notes video, but you'll notice there's a relationship. For angle H, the sine was 4/5, but when we change to the other angle in the triangle, the other acute angle, that 4/5, which was the sine for H, now becomes the cosine for the other angle. What was the cosine for one angle, 3/5, is the sine for the other angle, right? So the sine and the cosine kind of change places when we change angles. And then what happens with tangent is it goes from being 4/3 to 3/4. So the tangent ratios are the reciprocals of each other. Now in this second example, we're going to kind of take things up a step. We're going to take a look at why sine, cosine, and tangent can be really useful for us. In the previous example, we were just identifying what those sine, cosine, and tangent ratios would be for a certain triangle. Now we're going to take a look at how we might use those. So you'll notice here I have a triangle. It's a right triangle, and I know that one of its angles is 62 degrees. I could figure out what its other angle is pretty easily. I could just take 90 minus 62 if I wanted to figure out that angle. But what I'm actually trying to figure out in this problem is what is this length? Now, it's a right triangle, so some people might think I would use the Pythagorean theorem. But if I wanted to use the Pythagorean theorem, I would run into a problem because I would have two sides that are unknown. And so my Pythagorean theorem equation would not be able to be solved because it would have two unknowns. I can't use 30, 60, 90 triangle, the 30, 60, 90 triangle idea because it's not a 30, 60, 90 triangle. It's actually a 28, 62, 90. And we don't have a special specific pattern for 28, 62, 90 like we do for 30, 60, 90. But we can use the fact that this is a 62 degree angle to figure out exactly how long this would be. All right, and it's going to look like this. I'm going to use my calculator over here, and I'm going to figure out what the sine of a we're actually going to be using cosine. I'll tell you why in a second. I'm going to figure out what the cosine of a 62 degree angle should be. Because sine, cosine, and tangent are almost like the fingerprints for certain angles. Every angle measure, 62 degrees in this instance, has a very specific value for sine, it has a very specific value for cosine, and it has a very specific value for tangent. It's almost like its fingerprints. No two acute angles are going to have the same set of fingerprints. They're not going to have the same set of values for sine, cosine, and tangent. It's unique for every one of these acute angles that I might have in a triangle like this. Your calculator, your scientific calculator, knows exactly what that value should be. It knows what the sine of 62 should be, it knows what the cosine of 62 should be, and it knows what the tangent of 62 should be. I can use that knowledge to figure out what this missing value would need to be so that these two sides end up in the right ratio, the correct ratio for this angle. So let me kind of walk you through how I'm going to do this. I'm going to look at my triangle, and I'm going to label the parts of this triangle from the perspective of the 62 degree angle. Meaning I'm going to say that this is the hypotenuse, this is the opposite leg, and then this is the adjacent leg. And I'm going to look at this and say, okay, if I set up a ratio that's opposite over hypotenuse, the sine ratio for 62, that would involve this side and the side that I know. If I set up the cosine for 62, that would be this one. So let me write this out actually. I would know that the sine of my 62 degree angle would be the opposite leg length over 18 of the hypotenuse. I know that the cosine ratio for my 62 degree angle should be that x over 18 because that's the adjacent over the hypotenuse. And I know that the tangent ratio for my 62 degree angle would be the opposite leg divided by that x, the adjacent leg. So if I look at these three things, I'll notice that, hey, this one right here, I can actually solve this. I can use some math strategies, and I can figure out what this x would have to be so that the cosine of 62 is that number over 18. All right, so if this is a little bit confusing, just bear with me a second. I'm going to grab my calculator, and I'm going to type in cosine 62. So I'm going to hit this cosine button and then 62 on my calculator. And what that's going to give me is it's going to give me a very long decimal number. It should say, if you type that into your calculator, you should get 0.469471562.8 or something like that, which is what should show up on the screen. So that is the very specific value for what cosine of a 62 degree angle should be. The cosine of a 62 degree angle should be 0.469471562.8, and actually if our calculator had more space it would probably even go on past that. That's the very specific fingerprint, if you will, for this 62 degree angle. It's its cosine fingerprint. Well, if I look at this equation that I wrote says that the cosine of my angle in this picture is this mystery side over 18. There's only one number that I would put in there so that when I divided it by 18, I would get this amount. So I can find that. I can figure out what number would go right here so that when I divide it by 18, I get this. And let me show you how I'm going to find that number. I'm going to come back here. I'm going to come back to this cosine 62 equals x over 18. I'm just going to rewrite it over here. Okay, cosine 62 equals x over 18. And I'm going to think about that cosine of 62 being over 1. Right? So now it looks like a fraction. I have cosine 62 over 1 equals x over 18. Now this cosine 62 is actually this amount. It's this weird decimal amount, but rather than writing that, I'm just going to write cosine 62 because it's shorter and easier to keep track of. But I have a fraction equals a fraction. And when I have that, I can cross multiply. If I cross multiply this, I end up with x times 1 equals 18 times the cosine of 62. And x times 1 is just x. But if I grab my calculator and I type in 18 times cosine 62, that's going to be my value for x. So let me do that real quick. 18 times cosine 62 gives me about, I shouldn't say equals, let me say about right there. Okay, let me erase my equal sign because I'm going to round this. I'm going to say my x is about 8.45. So that's the approximate value for x, that when I divide it by 18 gives me the correct fingerprint, if you will, for this 62-degree angle. If I wanted to find this side, I would just use the same idea here, but I would use my sine ratio. For instance, if there was maybe there was a problem where there was another variable here, maybe there was a y right there, then I would do the same idea, but I would use sine 62 equals y over 18, and then I would work it out the same as what I did here, only using sine of 62 instead of cosine. And that's what we can use this SOHCAHTOA stuff for. We can look at a triangle where we don't have enough information to use the Pythagorean theorem, and we don't have enough information to use like a 30-60-90 or a 45-45-90 trick, and we can still find a missing side.